So in the last class we had talked about Eulerian and Lagrangian description. What is a field? Field is a distribution of a variable over space and time. You can have temperature field, pressure field. So you have to give value of temperature and pressure over space, over XYZ coordinates. Now I'll take an example of particle going around in a circle. So, so this particle is going around in a circle. It has an angular velocity omega. So it is going around at a constant angular velocity. So what is your angular velocity? Omega k. Now what is this radial vector? You can connect it. This is ER. This is your radial vector pointing outward. This is your theta. And this is a tangential vector E theta. So you have got 3 unit vectors. If you go use polar coordinates, ER, E theta, K. These are your 3 unit vectors. One is along radial direction, one is along theta direction. This angle is 90 degrees. Then you will see ER cross E theta is equal to K. So these are your unit vectors. Now what is the position vector of point A? Particle is at point A. This is a position vector. So the position vector becomes in this case R E R. The particle is going around in XY plane. So what is the velocity of the particle? Can somebody tell me? Velocity of particle. Yes.
Yes.
Yes. Anybody?
R cross omega, sir.
Yeah.
So omega into
Sir, omega R.
What is the direction?
Sir,
You have to tell the direction.
R cross omega.
You see, direction is tangential to the path.
yes, sir.
It is going a circular path. So what is the direction? What is our tangent at this point? Okay. What is your ER vector? Yeah.
Three.
What is the ER vector? All right. What is your E theta vector?
Cos theta.
Any problem? हेलो अरुण जी मैं थैंक यू सेम टू यू 1 घंटे बाद बात करें ओके ओके थैंक यू So what is the velocity then? Omega r into minus sine theta I plus cos theta j. So this becomes So this becomes r sine theta is y minus omega yi plus omega xj. Any problem? So you get velocity of particle at point A. What is acceleration of particle?
Omega square r.
You never give only omega square r. You have to tell the direction. It's a vector.
Sir, ER
Er.
minus here.
minus.
Very good. So this is equal to minus omega square r. Er is cos theta sine theta 0. So you get minus omega square x y 0. All right. So this was Lagrangian description of the particle motion. You gave the motion of the particle. You logged on to the particle and you told that particle is going around in a circle. You knew its r, you knew, then you found its velocity by simple differentiation with time, and also you found the acceleration by a simple derivative with time. Now you see your velocity you have written as this is a velocity. Suppose instead of a particle you had a rigid body which is spinning around. So if your particle is here, if you are at this position, this is the velocity. At any position you can find velocity in space. Any problem? By this description, by this formula. So you can say this is your spatial description. At any point in space, you just give xy coordinates and you come to know if the particle was at this position, this is the velocity. Okay. So now we want to find, now this is an Eulerian approach. Now we want to find the acceleration. Our description of the velocity field is spatial. Okay. Or Eulerian. We are not describing the velocity of a particle. We are just giving the velocity in space. If the particle occupies certain position, this is the velocity. We are not chasing the particle. You see in fluid mechanics, you have got a pipe flow. So it is difficult to chase each particle. So you just give over this volume, you give some velocity description. So velocity description is a field. It's over space and time. You don't tell which particle. You tell if the particle is here, this is the velocity. If particle is here, this is the velocity at this point of time. So it depends on position and time. Now your velocity is a function of x, y, z and time. So how do you find dv? So if you are here from here to here, suppose you chase the particle, it goes from here to here. But you know description is, if it is here at this point of time, this is the velocity. And if you want velocity at x plus delta x in time delta t, it travels. It goes to its x and y z coordinate change by this amount. What will be delta x? You say your velocity vector is Any problem?
No, sir.
No, sir.
So now, what will be my simple Taylor's theorem you use? Any problem? So your velocity is a function of x, y, z, and t. So you use all those variables. Some increment in t, some increment in delta x, delta y, delta z, and velocity derivatives. Any problem? So if you just want to find acceleration, so you have to take this to the left hand side. So this becomes change in velocity of that particle, which was initially here, finally here. So you want to find material derivatives. You are finding a material derivative. Material derivative means you are locking onto the particle using a spatial description of the data. Your data is given in spatial form. Okay, you're not given how that particle is moving around. You are just told this is a velocity field in space. So what is it? So this subtraction, and then you divide by delta t throughout. So you get material derivative of velocity or acceleration of the particle. So this is acceleration of a particle. So you get delta v by delta t. So what do you get? So this you can write as vector v dot gradient of velocity. You see, what is this term? This is basically gradient of velocity. And what is this v dot delta? v1 del by del x, v2 del by del y, v3 del by del z. Any problem with this? You could have also written it as gradient of v multiplied with v. Any problem?
No, sir.
It's like a dot product. Product. This is one thing, but this is not a vector. This is a matrix, and this is a vector. So you multiply matrix and a vector, you get a vector. Acceleration is a vector. You see, each term has to be a vector. You see, this is a scalar. These are two vectors. Gradient is a vector. Velocity is a vector. So you're getting a vector. Both things are equivalent. There is no problem. Now we look at our velocity field, which we found for a rotating body. You assume there is a body rotating with angular velocity omega about this origin. So we found that velocity of any particle in space at x, y, z. This velocity was omega r into e theta, and e theta was cos 90 plus theta, comma sine 90 plus theta, comma 0. Particle is going around in xy plane. So you get minus omega y. This was 90 plus theta sine 90 comma omega x comma 0. So now you have got your velocity as a spatial field. You put the values of xy coordinates and you get the velocity. Now we found the acceleration formula as del v by del t plus gradient of v into v. Now what is gradient of this vector? Any term, ijth term will be given by vi comma j. So what is this matrix? Del v1 by del x1, del v1 by del x2, del v1 by del x3, del v2 by del x1. If you listen to my lectures, these things will become easy for you. Whatever I have uploaded at YouTube, a lot of this stuff is already done there.
Okay, sir.
Any problem with this? I have given one term of this. I have described it as this. So my gradient of V is this. This I use in either I put it for a vector something below it or above it. This is quite a standard way of doing it. Hello. So now we have to find this. So what is del V1 by del X1? This is a V1, so it is 0. Del V1 by del X2 minus omega. Del V1 by del X3 0. Del V2 by a del X1 omega. Del V2 by del X2 0. 0. So these are all zeros. So you got your gradient of velocity vector. So now you see all my terms are independent of time. We have assumed omega is constant. Angular velocity we have taken as constant. So what is my del dv by dt? Now because del v by del t is 0 plus gradient of v into v. So what do you get? 0 minus omega 0, omega 0, 0. हेलो मैडम 1 घंटे बाद बात करें. गुड मॉर्निंग मैडम. 1 घंटे बाद बात करें. ओके थैंक यू. ओके. So what is the velocity vector? Minus omega y, omega x 0. So you have to just do a matrix multiplication. So you get minus omega square x Second row you multiply minus omega square y. So you see this looks like minus omega square. So you're getting minus omega square is it all right?
Yes.
Yes,
So
sir.
this is what you expected. Minus x minus y 0 is your minus ER. So that I have used. So you see now how to go from, if you are given a spatial description, you can find material time derivative of any vector. Okay. Okay. What is A cross B cross C? Anybody remembers?
Sir, A dot C into B plus A dot C minus A dot B into C.
First thing is, you see, this is something perpendicular to B plane made by vector B and C. This will give you a vector perpendicular to plane made by vectors B and C. Once you take cross product with A, it means your vector lies in the plane made by B and C. Is it okay?
Yes, sir.
So you should get B. You can just verify whether this is all right. What you do, I and J. So what is I cross J is K. I cross K is equal to minus J. You have to just check it out. A dot C, I dot J is 0. And here you get minus C, J. And sorry, B A dot C minus C A dot B. And this is I dot I. This is 1. So you get minus J. So your formula is all right. Usually there is an issue of this sign, whether you have to write this first or that first. So now this is done. Now what I want to find is V cross del cross V. What this will be equal to. Yes, anybody? Will someone like to help me out?
Sir, could you please repeat?
What is this equal to? You already have a formula at the top. So we use gradient A dot C, V dot V. Then minus C C is V, A dot B. A dot B is like V dot gradient. So what does it mean? Gradient of V into V. Can you write it gradient of half V square? I'm just checking out.
Yes.
Suppose this can be written as, I'm just checking out. Let me see what happens. Now this is okay. Let it be like what it was earlier. So this is, you can see, you can identify it. Divergence of velocity into V. That doesn't look good to me. So if it is like this, what is a dV by dt? Is equal to del V by del T plus
B dot del.
V dot gradient into V. That's the way you had written.
Yes, sir.
So what do you get? So this, now how can you write this like this? Suppose you take its, we pick this term, gradient of half V square. V square is nothing but V dot V. So if you take its derivative, its gradient. So it looks like half you take outside. Gradient of V dot V plus same thing again, V dot gradient of V. So you're getting gradient of V dot V. So you can write this term as this, not an issue. So what do you get? So del cross V is equal to gradient of half V square. So there was a minus sign. So we want this term minus dV by dt plus del V by del T. So you can write dV by dt is equal to gradient of half V square minus, sorry, this was V cross del cross V. plus V cross del cross V plus del V by del T. Any problem with this? So this is known as, this is curl of velocity field.
So can you explain the gradient of half v square once again?
Okay, gradient of half V square. So it is gradient of half V dot V, or you could have directly written half V square. What is its derivative? Half into 2 into V. So V is a scalar here, magnitude of velocity,
Yes.
into gradient of V. So you get,
Okay, sir. Yeah.
so
That will get cancelled.
that is a problem, I think. It is better to go like this. Then what do you get? Half V dot gradient of V, then twice of it. So you get gradient of V dot V. Where I was. So basically I had replaced gradient of V dot V with this term. All right. So I'm getting gradient of V dot V. It's a dot product. So you can, it is better written like gradient of V dot V because it's a matrix product. This is a matrix of order, tensor of order 2. So this has to multiply with a vector. Only then you will get a vector. Is it all right?
Yes, sir.
Okay. There is one more thing I'll tell you. Suppose you have got something called AX. So how can you represent this product? This is some vector Y. So can you write yi is equal to aij xj? So you can also write it as xj aij, and this you can write as xj whenever you do any matrix multiplication, you try to match the index. Here you match j and j. Here it was not matching, so you did a transpose. So let us see whether it is fine. Suppose you take a matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, and you multiply with something like 1, 0, 0. What will you get? You will get the first column. Now suppose I write it as in this form. So I got 1, 0, 0. Then I write its transpose. So what is the transpose? 1, 5, 9, 2, 3, 4, 5, 6, 7, 8, 9. So you're just changing rows into columns. Now can you multiply these two matrices? So this is 3 by 1, sorry, 1 by 3. This is 3 by 3. So you can multiply
Yes, sir.
So if you multiply it, what do you get? 1,
1 cross 3.
you get 1. Again you multiply.
Sir, first matrix is 3 by 1, I guess.
Okay, sorry. So you have to write it in a, you have to put the vector like this. Okay.
Yes, sir.
It's a vector. Its transpose is equal to itself. Not an issue. If I do like this, what will happen? Then 1, I get 1. Then second time I do, I get 4. Third time I do, I get 7. So this is my vector 1, 4, 7. Same thing, same vector. So this thing comes handy at many times. Y is equal to Ax is equal to X A transpose. Whenever I use a tensor of order 2, I put 2 bars below it. If it is a vector, it is 1 bar. If it is a scalar, nothing. So that's the way we distinguish between tensors of different order. Okay, so I found dv by dt as this. So what is the advantage of doing like this? Suppose I take gradient of this term. If I take gradient of it, what will happen? What is the meaning of gradient? You are just multiplying with grade and you are taking the derivatives of any quantity with x, y, z. So what is gradient of dv by dt? So basically it will be d by dt of gradient of v. Any problem? Oh,
No, sir.
okay. Okay, not an issue. Okay, let's, instead of doing like this, I do something different. I call v is a gradient of some function phi. If I do like this, v is gradient of some scalar phi. Now v is a velocity. Once something is a velocity, if I say it is a gradient of some function phi, then it is a scalar quantity, phi is a scalar. So you get a vector field. Such a thing you can do when there is a potential flow. We'll learn what is a potential flow. If any field variable you can describe as gradient of something, it is called a potential function. Have you seen it before, potential function? In
No, sir.
gravitational field, you have seen it. You see, you say gravitational field is gradient of a potential. How to define gravitational force? As the gravitational force is minus gradient of phi. So that is why you call it a potential field. You see, you say phi is your mgz. If your phi is mgz, you are measuring your z like this. So higher you are from the datum, higher the potential energy. So what is the gradient of phi? 0, 0 mg. There is a minus sign. So you see a gravitational force is downwards. So you can describe gravitational force as gradient of a potential energy. So this is a potential or potential energy. In this case, you call it potential energy. Here we just call it a potential function phi. If you can describe velocity by this kind of a description, you call your flow as potential flow, where velocity is given by gradient of some scalar. If that is happening, what will happen? Now you see del cross V, del cross of gradient of phi. Have you heard? Have you seen such a quantity? Gradient cross gradient. You see, it is looking like two same vectors. Gradient cross gradient. So this has to be zero. Like I cross I is zero, J cross J is zero. Similarly, if you do cross product of a gradient, you will get a zero. Maybe we can even check it out. So what is your gradient of phi? Del phi by del x, del phi by del y, del phi by del z. So what this becomes? I, j, k. What is gradient? Del by del x, del by del y, del by del z. So we have to check it out whether this gives you a zero. So you look at I, del square phi by del x square by del x del y. Again, you see this term is zero. Similarly, you will find other terms also going to zero. So this term is zero. So if you go back to that, so you see you have knocked out one term. So you get d by dt. Velocity is gradient of I is equal to gradient of half v square. This is anyway a scalar, so we don't mind it. We don't play with it further. This goes to zero. And if your velocity, if your field is steady, there is something called steady. Steady means things don't change with time. So this is something called a local time derivative. Suppose you have a field here. Liquid is flowing through this pipe. And you say your field stays same throughout. With time it is not changing. So you don't have time as a variable. So this del v by del t will go to zero. And if you are having, here you can write gradient of phi. So you are getting plus gradient of del phi by del t. In case this is zero, this derivative is zero, this term is a zero. So you have converted this acceleration into gradient of some terms. Okay. Any questions? one more simple basic stuff I will talk. Suppose you are given F is equal to ma. So particle is accelerating under a force field. If you take its dot product with velocity, what do you get? What is this term? So see, time derivative of kinetic energy is equal to power input. This is your input power. Force dot product with velocity. So if there is any unbalanced force, this is your unbalanced force. Unbalanced force causes acceleration. So whenever you have unbalanced force, you generate kinetic energy. So in this course, we have got several important equations. So we will be dealing with some conservation laws. One of them is mass conservation. Then conservation of momentum, linear momentum, angular momentum, then energy. So we have to deal with all of them. This is nothing but Newton's second law. So Newton's laws are applied to a particle, rigid body, deformable solid. If you look at my lectures, all this is done already in YouTube lectures. And now in this course, you will see how they apply to a control volume. Basically, you see all Newton's laws are applied to a particle. You can't say something is this control volume is applied. This is just a concept. Only thing is from spatial description, how you go to material description. So from spatial, you have to go to material. You need material derivatives. So you see, you are given a velocity field in spatial form. What you found? dv by dt. So if you multiply it with rho, this is your net force per unit volume. Can you see that? Force is mass into acceleration. So per unit volume, the rho is density into acceleration. Now this has to be equal to unbalanced force. I told you if there is a pressure field, you will say minus gradient of P. That is a force applied by a pressure field. If there is some gravitational field, plus rho g. You see, this is gravitational force per unit volume. So this is one equation which is known as Euler's equation for fluid motion. So we'll carry on. The class is over.
Thank you, sir.
Okay.
Thank you, sir.
Okay. So you must go through all that, whatever I have taught.